the eternal mystery of the universe. Imagine yourself lying beneath a boundless dark ocean, but instead of water, it is the endless expanse of space. Above, an infinite tapestry of stars glimmers, each a distant sun, their light having travelled eons to reach your eyes. The air is still, carrying a profound coolness, and with it the scent of eternity itself. This celestial panorama, the night sky, has forever pulled at the human spirit, hasn't it? That deep, resonant feeling of awe, of a mystery just beyond our tangible grasp, has echoed through humanity since our very first conscious thoughts. We are, by our very nature, explorers of the unknown, innately driven to map its shores, to understand its depths, and the universe, with its endless, layered enigmas, is perhaps the ultimate ocean to navigate, the ultimate mystery to contemplate. Consider the cosmos as an ancient, sprawling library, but one unlike any you've ever encountered. Its shelves stretch into unimaginable infinities, holding volumes with no discernible beginnings, no definitive ends. Each page, turned within these cosmic tomes, reveals wonders more perplexing, more beautiful than the last. What we've managed to read so far, the knowledge we've painstakingly gathered through centuries of observation and thought, amounts to but a handful of chapters in this immeasurable, boundless collection. It is a grand library, brimming with unwritten sagas, unsolved riddles, and truths that shimmer tantalizingly, always seeming just out of our full reach. At the very heart of this cosmic library, etched into its foundational stone, is a question, a single, profound query that has captivated thinkers, scientists, poets, and mystics for millennia. Why is there a universe at all? It presents itself as a deceptively simple inquiry, yet the more one allows the mind to dwell upon it, the deeper its currents pull into oceans of thought without a flaw. Why is there something, this incredible, complex, dynamic reality, rather than an absolute, unyielding, eternal nothing? This question forms the very bedrock of all we comprehend. As you sit with this question, it's easy to feel the immense, almost crushing gravity of its scope. We are but fleeting, delicate beings, ephemeral sparks of consciousness, attempting to perceive and understand a reality that extends far, far beyond the limits of our senses, beyond the grasp of our current tools. This is the essence of what we might call the eternal mystery of the universe. The cosmos, in its staggering, almost terrifying vastness, operates on scales of time and space that our human minds can barely brush against, let alone fully internalize. It is ancient, so profoundly ancient that the human intellect falters, stumbles, trying to truly grasp the sheer depth of its age. Billions of years, the number sounds grand, impressive, yet it fails to convey the true experiential meaning. What is the texture, the feel of 1 billion years? How can one truly quantify or internalize something that existed eons before life, as we recognize it, flickered into being on this small planet, and will persist in some form long after our fleeting human presence has faded into the cosmic dust? It's akin to envisioning a path that stretches infinitely in both directions. You acknowledge its existence, its theoretical continuity, but you can never see its totality, never truly grasp its full, unimaginable extent. The mystery lies not just in its incomprehensible immensity, but in its very persistence, its being. The universe feels timeless, eternal, always present, yet always shimmering just beyond the cusp of our complete and final understanding. Picture this. If you were to zoom out from your current vantage point, far beyond our solar system, past the swirling, graceful arms of our Milky Way galaxy, beyond the superclusters of galaxies that weave the intricate cosmic web, you would still only be glimpsing a mere fragment of the conceivable whole. No matter how far your perspective travels, no matter how much knowledge is accrued, there is invariably more to discover. More stars, more planets, more bizarre and beautiful phenomena that challenge the very foundations of our established knowledge, pushing the boundaries of our understanding ever out. But here, the narrative of our relationship with the universe takes an even more intimate and intriguing turn. The deeper we delve into the cosmos, the more we meticulously observe its workings, the more we realize that we are not merely detached observers looking in from the outside. We are intrinsically, fundamentally part of it. The very atoms that constitute your being, the carbon, the oxygen, the nitrogen, the elements that form everything around you, were forged in the incandescent, fiery hearts of stars that lived, shone, and died in cataclysmic explosions billions of years ago. We are quite literally composed of stardust. In this profound and beautiful sense, the universe isn't just out there, separate, distant, and alien. It is also in here, within us, flowing through us, an inseparable part of our very existence. This intimate, undeniable connection between the cosmic vastness and our own fleeting conscious existence brings us full circle back to the embrace of the eternal mystery. We are simultaneously spectators of this grand cosmic drama and active participants within it. Our thoughts, our actions, our art, our science, our very being are interwoven with the cosmos in ways we are only just beginning to truly unravel and appreciate. And for all that we have learned, for all the incredible progress we have made in understanding our universe, so much remains veiled, hidden in the cosmic shadows. What lies beyond the observable edge of our universe? What, if anything, preceded the Big Bang, the moment our current cosmic epoch began? Will the universe continue to expand forever? Or will it, one day perhaps, conclude its epic, unfolding tale in some yet unknown fashion? These are the grand questions that propel us, that ignite our curiosity, that drive us to explore, to seek answers, even with the humble understanding that some mysteries may remain forever unsolved, forever beyond our ultimate grasp. The eternal mystery of the universe is not something to be feared, nor is it a sign of our insignificance. Rather, it is an open, standing invitation to embrace wonder, to cultivate curiosity. It's a profound reminder that we are part of something far, far larger than ourselves, something that transcends the limitations of our current comprehension, something magnificent. It's an open call to keep questioning, to keep seeking knowledge, to keep dreaming, and to remain in perpetual humble awe of the world that surrounds us, includes us, and indeed is us. As you drift towards the gentle shores of slumber, let this feeling of profound wonder wash over you, like a calm cosmic tide. The universe may be vast, its mysteries without apparent end, but you are an integral, conscious part of it, and in that undeniable connection there is an inexhaustible beauty, there is profound meaning, and there is the endless, thrilling promise of discovery. Cosmic microwave background. Imagine yourself enveloped in an utterly silent, perfectly dark chamber. So quiet, in fact, that you might begin to perceive the faintest, almost imperceptible hum, perhaps the sound of your own body, or the residual echo of the world outside. Now, expand that sensation. Picture that subtle, pervasive hum not confined to a single room, but permeating the entirety of existence, filling every cubic centimeter of the vast, empty reaches of space with a faint, persistent, ancient resonance. This is not mere fancy. This is a reality. This cosmic hum is a remnant, an afterglow from the universe's earliest fiery moments, an echo of the Big Bang itself. This is the cosmic microwave background, or CMB, one of the most profound and elegantly revealing discoveries in the entire history of modern cosmology. To truly understand and appreciate the significance of the cosmic microwave background, let us embark on a journey back through the mists of deep time. Picture the universe as it was approximately 13.8 billion years ago, when it was still an utter infant, a mere blink of an eye after its cataclysmic birth. Back then, the cosmos was nothing like the relatively cool, dark, and structured expanse we observe today. Instead of stars, galaxies, and planets, it was a seething, unimaginably hot, and incredibly dense soup of fundamental particles, protons, neutrons, and electrons, all colliding frenetically with photons of light in a chaotic, incandescent dance. The universe at that time was completely opaque, a blinding superheated plasma where light couldn't travel more than a microscopic distance without bumping into a charged particle and being scattered. It was like trying to see through the densest, most luminous fog imaginable, a fog that filled all of space. As this primordial soup of a universe expanded, it also began to cool, much like a hot goss cools as it expands. Around 380,000 years after the Big Bang, a truly extraordinary and pivotal event occurred. The universe had cooled down enough to a temperature of about 3,000 Kelvin, roughly the surface temperature of a cool red star, for protons and electrons to finally combine and form stable, neutral hydrogen atoms. This process is known as recombination. With far fewer free, charged particles around to scatter them, photons of light were suddenly set free, liberated to travel unimpeded through the now transparent space. For the very first time, light could journey across vast cosmic distances without being constantly deflected. This momentous event is sometimes called the epoch of last scattering. The light that was set free at that precise time, at that specific moment in cosmic history, still exists today. That ancient, liberated light, stretched and cooled by billions of years of cosmic expansion, is what we now detect as the cosmic microwave background. Think of the CMB as the universe's very first photograph, a baby picture capturing its likeness when it was still in its earliest infancy. Just as a precious photograph of a newborn captures a fleeting moment in time, the cosmic microwave background shows us the universe as it looked when it was a mere 380,000 years old, a fleeting instant in the grand sweep of cosmic terms, but a crucial one. It's an image frozen in time, giving us a direct glimpse into what the universe was like when it was on the cusp of transitioning from a hot, uniform plasma to a cooler, neutral gas. out of which all future structures would eventually form. Now, here's where the CMB becomes even more fascinating and informative. When we observe the cosmic microwave background today with our sensitive radio telescopes and spaceborne observatories, we are not just seeing a perfectly uniform, smooth glow across the entire sky. This ancient light, though incredibly faint and having cooled to a mere 2.7 Kelvin, just 2.7 degrees above absolute zero, is not perfectly featureless. Instead, it contains incredibly tiny fluctuations, minuscule differences in temperature from one spot on the sky to another. These temperature variations are incredibly small, only a few parts in 100,000, mere microkelvins of difference. Yet, these almost imperceptible temperature fluctuations, they are the primordial seeds, the subtle density variations in the early universe, from which everything we see in the cosmos today, all the galaxies, all the stars, all the planets, and ultimately even us, grew under the relentless influence of gravity over the subsequent billions of years. It's like looking at a vast, gently simmering pot of soup as it cools. At first, the surface might look almost perfectly smooth from a distance, but upon closer, more detailed inspection, you would notice tiny ripples, subtle currents, and slight variations in temperature across its surface. These slight variations in the CMB are believed to be the macroscopic echoes of quantum fluctuations that occurred in the very, very early universe, perhaps during a hypothesized period of incredibly rapid expansion known as cosmic inflation, which is thought to have taken place mere fractions of a second after the Big Bang. These quantum jitters were stretched to astronomical scales by inflation, imprinting these subtle density differences onto the fabric of the early cosmos. Fast forward billions of years, and those tiny, almost insignificant ripples in the temperature of the CMB have evolved under the patient sculpturing of gravity into the vast, intricate cosmic web of galaxies, clusters of galaxies, and immense voids that fill the universe today. The same light that was once scattered and blocked within a hot, opaque plasma now passes through the transparent universe largely unhindered, giving us this precious snapshot of the universe at a time when everything we know today was just beginning to take shape, when the seeds of all future cosmic structure were just being sown. And the CMB isn't just a pretty picture, though its all-sky maps are indeed strikingly beautiful in their own way. It is one of the most important, robust, and compelling pieces of observational evidence supporting the Big Bang theory. When scientists like George Gamow, Ralph Alpher, and Robert Herman first predicted the existence of this ancient radiation in the 1940s, based on their models of an expanding cooling universe, they had no idea it would eventually be detected. But in 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon it entirely by accident. They were trying to eliminate a persistent, annoying background noise from their new horn radio antenna. After meticulously ruling out all possible terrestrial and instrumental sources, they eventually realized that this persistent, isotropic hum was, in fact, the cosmic microwave background, the very first direct observational evidence of the Big Bang. For their serendipitous and monumental discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. Today, The meticulous study of the CMB has become a cornerstone of modern precision cosmology, a succession of increasingly sophisticated space missions, see COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Analysis. These detailed observations have allowed scientists to determine key cosmological parameters with unprecedented accuracy, revealing crucial information about the universe's age, approximately 13.8 billion years, its overall composition, about 5% ordinary matter, 27% dark matter, and 68% dark energy, and its geometry, remarkably flat on large scales. In essence, the cosmic microwave background is a precious cosmic relic, a faint, lingering glow from the very birth of the universe. It continues to illuminate the darkest, most distant corners of space and time. It's a profound reminder of where we came from, a testament to a time when everything we see and know today was packed into an incredibly hot, dense, and uniform state, just waiting for the conditions to be right to unfold into the magnificent, complex, and evolving universe we now call home. As you drift into sleep, let the thought of this ancient light, this whisper from creation, still traveling tirelessly across the cosmos after nearly 14 billion years, bring you a deep sense of connection to the vast, mysterious, and ultimately knowable universe we inhabit. The expanding universe. Imagine yourself standing in the still, dark heart of an immense, featureless plain. All around you, scattered at various distances, are countless faint, flickering campfires. As you watch them over a long period, you begin to notice something truly extraordinary. All the campfires, in every direction you look, appear to be slowly but steadily moving away from you. And even more curiously, you observe that the farther away a campfire is initially, the faster it seems to be receding into the distance. This isn't because you are somehow repulsive, or because the campfires are actively trying to flee from your presence. Instead, it's as if the very ground of the plain itself, the fabric of the space between you and the campfires, is stretching, carrying these distant lights along with it, like raisins embedded in a rising loaf of bread. This analogy, though imperfect, offers a glimpse into one of the most profound, transformative, and initially startling discoveries in the history of science. Our universe is expanding. The galaxies, like those distant campfires or raisins, are not necessarily flying through a pre-existing, static space away from us. Rather, the very fabric of space itself is expanding between them, inexorably pushing them farther and farther apart, over cosmic timescales. The idea of an expanding universe is now a cornerstone, a foundational pillar of modern cosmology. Yet for millennia, the prevailing view, inherited from ancient Greek philosophers and reinforced by centuries of observation that seemed to show a stable, unchanging celestial sphere, was of a static, eternal, and finite cosmos. It wasn't until the early decades of the 20th century that astronomers and physicists began to uncover compelling observational and theoretical evidence that dramatically challenged this ancient and deeply ingrained notion. By meticulously studying the light from distant celestial objects, then known as spiral nebulae, which we now know are other galaxies, vast island universes of stars in their own right, astronomers like Vesto Slipher in the 1910s made a startling observation. The light from most of these nebulae was red-shifted. This means that the characteristic spectral lines in their light, like fingerprints identifying the elements present, were shifted towards longer, redder wavelengths compared to the same lines observed in laboratories on Earth. This redshift is analogous to the Doppler effect for sound. Just as the pitch of an ambulance siren sounds lower, longer sound waves as it moves away from you, the light from an object moving away from us is stretched to longer wavelengths. Slipher found that the vast majority of these nebulae were indeed receding from us, and some at very high speeds. Then in the 1920s, building upon Slipher's work, and using newly available, more powerful telescopes like the 100-inch Hooker telescope at Mount Wilson Observatory, Edwin Hubble, along with his assistant Milton Humason, made a series of crucial observations. First, Hubble definitively established that these spiral nebulae were indeed distant galaxies, far beyond the confines of our own Milky Way. Then, by carefully measuring both the distances to these galaxies, using Cepheid variable stars as standard candles, and their recessional velocities from their redshifts, he uncovered a remarkable and systematic pattern. The farther away a galaxy was, the faster it was receding from us. This clear linear relationship between a galaxy's distance and its recessional velocity became known as Hubble's law, now often referred to as the Hubble-Lemaitre law, acknowledging the earlier theoretical work of Georges Lemaitre. This was the smoking gun, the compelling observational evidence that the universe as a whole was not static, but was indeed expanding. The expansion of the universe was, in fact, a natural consequence of Albert Einstein's groundbreaking theory of general relativity, which he had published in 1915. Einstein's complex field equations, which described the intricate relationship between gravity, matter, energy, and the geometry of space-time, actually predicted that a universe filled with matter could not be static. It should be either expanding or contracting. However, Einstein himself, deeply influenced by the prevailing scientific and philosophical belief in a stable, unchanging universe, initially resisted this implication of his own theory. He even went so far as to introduce an arbitrary cosmological constant, a kind of repulsive anti-gravity term, into his equations, specifically to force a static solution, a decision he later famously called his biggest blunder after Hubble's observational confirmation of the expansion. The discovery of the expanding universe had immediate and profound implications for our understanding of the cosmos's origin and evolution. If the universe is expanding today, it logically implies that it must have been smaller, denser, and hotter in the past. If you run the movie of cosmic expansion backward in time, all the matter and energy in the observable universe would eventually converge into an incredibly hot, dense, and unimaginably small state. This line of reasoning led directly to the concept of the Big Bang, the prevailing cosmological model, which posits that the universe began approximately 13.8 billion years ago from such an extreme singular state, and has been expanding and cooling ever since, eventually leading to the formation of the atoms, stars, galaxies, and complex structures we observe today. The expansion of the universe continues relentlessly to this day, and it's happening on the grandest of cosmic scales. It's important to note that this expansion is not like an explosion of matter into a pre-existing empty space. Rather, it is an expansion of space itself. Galaxies are not like shrapnel flying through a void. They are more like points on the surface of an inflating balloon, being carried apart as the balloon space itself stretches on smaller gravitationally bound scales within our solar system, or within our Milky Way galaxy, or even within our local group of galaxies, which includes the Milky Way, Andromeda, and a few dozen smaller galaxies. Gravity is strong enough to overcome this cosmic expansion, keeping these structures intact. But on larger intergalactic scales, the expansion of space becomes the dominant force, driving galaxy clusters farther and farther apart. One of the most surprising and still deeply perplexing aspects of the expanding universe is the discovery made in the late 1990s that this expansion is not slowing down, as one might expect, due to the gravitational pull of all the matter in the universe, but is actually accelerating. Two independent teams of astronomers studying distant peak brightness serve as excellent standard candles for measuring cosmic distances, found that these ancient explosions were dimmer and therefore farther away than they should be if the universe's expansion was constant or decelerating. This implied that the expansion of the universe has been speeding up over the past 5 to 6 billion years. This was a shocking and revolutionary discovery, earning the leaders of these teams the Nobel Prize in Physics in 2011. The cause of this cosmic acceleration remains one of the biggest unsolved mysteries in all of science. To explain it, physicists have postulated the existence of a mysterious, all-pervading form of energy with repulsive gravitational properties, dubbed dark energy. This dark energy is thought to make up about 68% of the total energy mass density of the universe, dwarfing both ordinary matter, about 5%, and dark matter, about 27%. Despite its dominant influence on the universe's ultimate fate, the true nature of dark energy remains completely unknown, a profound enigma challenging our most fundamental understanding of physics. As the universe continues its accelerating expansion, the distances between gravitationally unbound galaxy clusters will grow ever larger. In the far, far distant future, galaxies that are currently visible to us will eventually be carried away beyond our cosmic event horizon, the boundary beyond which their light can no longer reach us, no matter how long we wait, due to the accelerating expansion of space. They will, in effect, disappear from our view forever. The night sky as we know it today, teeming with the faint smudges of distant galaxies, will look profoundly different billions upon billions of years from now, becoming increasingly empty and dark as the relentless expansion carries all but our closest galactic neighbors out of observational reach. It's a somewhat sobering, even melancholy thought, but it also underscores the dynamic, ever-evolving nature of our cosmic environment and the transient beauty of our current cosmic perspective. So, as you imagine those distant galaxies, like those flickering campfires on an ever-stretching plain, think of them not as static, fixed points of light, but as celestial voyagers being carried ever farther apart by the unseen yet inexorable currents of expanding space-time. The universe is not a silent, unchanging backdrop to our existence. It is a dynamic, evolving, and astonishing entity, and we are but privileged, fleeting observers, floating along in its vast, expanding and accelerating expanse. As you drift off to sleep, let the image of these receding galaxies, swept along by the quiet, persistent, and powerful tide of cosmic expansion, remind you of the constant, subtle, yet profound changes happening all around us, both on the grandest cosmic scales and perhaps in the unfolding narratives of our own brief, precious lives. The expansion of the universe is a silent, majestic, and accelerating dance, played out across the cosmic sea, carrying the islands of light farther and farther into the unknown future. Dark matter. Picture yourself, if you will, walking through a vast, ancient, and profoundly dense forest. As the twilight deepens into night, the towering trees around you merge into dark, imposing silhouettes against the last vestiges of the fading light, and you can only clearly discern what's immediately in your path. An almost preternatural quiet hangs heavy in the cool air, punctuated only by the occasional, unseen rustle of leaves in the high canopy, or the distant, muffled snap of a twig under some unseen creature's foot. You have a strong, intuitive sense that this forest is teeming with hidden life, birds nestled silently in high branches, nocturnal animals beginning to stir in their burrows, perhaps even larger, more elusive creatures moving stealthily through the undergrowth. But you cannot see them directly. You can only feel their subtle, almost subliminal presence, hear the faint, ambiguous evidence of their movements, and infer their existence from the subtle disturbances they create in the otherwise still, dark environment. Dark matter, in the grand cosmic scheme of our universe, is much like those unseen, hidden inhabitants of the twilight forest. It is an invisible, pervasive, and profoundly influential substance, or perhaps a collection of substances, something we cannot observe directly with any form of light or electromagnetic radiation, yet we know with a high degree of certainty that it's there, because of the profound and undeniable gravitational effects it has on the visible cosmos, on the stars, the gas, and the galaxies that we can see. Dark matter is, without doubt, one of the most significant, compelling, and deeply perplexing mysteries in all of modern astrophysics and cosmology. Unlike the familiar matter that makes up stars, planets, and ourselves, often called baryonic matter, dark matter does not appear to emit, absorb, or reflect any form of electromagnetic radiation, be it visible light, radio waves, X-rays, gamma rays, or anything in between. It remains completely transparent, ghostly, and elusive to all our telescopes and detectors that rely on light, yet, remarkably, based on a wide range of diverse and converging lines of evidence, astronomers estimate that dark matter makes up roughly 85% of the total mass in the entire universe. This means, astonishingly, that the vast majority of the universe's material substance is composed of something we've never directly seen, something whose fundamental nature remains a profound enigma. We know that dark matter must exist primarily because of its pervasive, and measurable gravitational influence on the visible matter and light that surrounds it. One of the earliest compelling clues that pointed towards the existence of this unseen mass emerged in the 1930s. The Swiss-American astronomer Fritz Zwicky, while meticulously observing the motions of galaxies within the Coma cluster, a large, dense collection of hundreds of galaxies, noticed something deeply puzzling. He found that the individual galaxies within the cluster were moving much, much faster than they should be, given the total amount of visible matter, stars and gas that he could account for within the cluster. These galaxies were zipping around at such high speeds that the gravity of the visible matter alone should have been far too weak to hold the cluster together. It should have flown apart long ago. Zwicky correctly inferred that there must be a tremendous amount of additional, unseen mass present within the cluster, providing the extra gravitational pull needed to bind these fast-moving galaxies. He dubbed this missing, invisible mass Dunkle Materie, which translates from German as dark matter. For several decades, Zwicky's observations, though prescient, were not widely accepted, partly due to uncertainties in the measurements of galactic masses and distances at the time. However, in the 1970s, the astronomers Vera Rubin and Kent Ford, and independently by others, provided even more striking and robust evidence for dark matter. This time from observations of individual spiral galaxies. They meticulously measured the rotation curves of these galaxies, that is, how fast stars orbit the galactic center at different distances from it. According to Newtonian physics and the observed distribution of visible matter, which is mostly concentrated towards the center of a galaxy, stars in the outer regions of these galaxies should have been orbiting much more slowly than stars closer to the galactic center, much like the outer planets in our solar system, like Neptune, orbit the Sun much more slowly than the inner planets, like Mercury. This is because most of the visible mass appears to be in the central bulge and disk. However, Rubin, Ford, and their colleagues found something completely unexpected. The stars in the outer regions of spiral galaxies were orbiting just as fast, if not sometimes even faster, than the stars nearer the center. Their rotation curves remained remarkably flat, out to the very visible edges of the galaxies. The only plausible explanation for this surprising and persistent behavior was that these galaxies must be embedded within vast, extended and invisible halos of dark matter, halos that contain much more mass than all the visible stars and gas combined. This unseen dark matter halo provides the extra gravitational pull needed to keep these fast-moving outer stars firmly in their orbits, preventing the galaxies from spinning themselves apart. Think of it like a spinning carousel or a merry-go-round. If all its mass were concentrated at the very central hub, the horses on the outer edge would naturally swing around much more slowly than those closer to the middle. But if there were a significant amount of unseen, distributed mass extending far out beyond the visible structure of the carousel, or even if an invisible, benevolent hand was gently but firmly holding on to each outer horse, they could all rotate at a more or less similar speed, regardless of their distance from the center. Dark matter acts like that unseen, extended mass, or that gentle, pervasive gravitational hand in galaxies, providing the necessary glue to hold everything together and explain their observed rotation. Dark matter doesn't just affect the dynamics of individual galaxies and clusters of galaxies. It plays an absolutely fundamental and indispensable role in the formation and evolution of all large-scale structures in the entire universe. Over the vast expanse of cosmic time, billions of years, the subtle but relentless gravitational influence of dark matter has shaped the very architecture of the cosmos in the early universe after the Big Bang. Ordinary matter, protons, neutrons, electrons, was hot and interacted strongly with radiation, which prevented it from easily clumping together under gravity. Dark matter, however, being non-interactive with light, could begin to collapse gravitationally much earlier, forming deep potential wells or gravitational seeds. Ordinary baryonic matter then fell into these pre-existing dark matter halos, eventually cooling and condensing to form the first stars and galaxies. Without dark matter, it's very difficult for cosmological models to explain how the structures we see today could have formed in the relatively short time since the Big Bang. Dark matter acts as a kind of invisible cosmic scaffolding, its gravity drawing visible matter into denser regions, which then ignited to become the galaxies, stars, and planets that populate our universe. Scientists have even been able to map the distribution of dark matter across vast cosmic distances by studying a fascinating phenomenon called gravitational lensing. This occurs when light from a very distant galaxy or quasar passes by a massive object, like a galaxy cluster, which contains a lot of dark matter, that lies along its path to us. According to Einstein's theory of general relativity, mass warps space-time and light follows these, so the gravity of the intervening massive object bends and distorts the light from the distant source, acting like a cosmic lens. By meticulously measuring how much the light is bent and how the images of distant galaxies are distorted, astronomers can infer the presence, distribution, and total amount of mass in the lensing object, including the dominant contribution from dark matter. Even though they can't see the dark matter directly, these studies have revealed immense interconnected filaments, sheets, and vast, roughly spherical halos of dark matter stretching across the cosmos, forming the underlying invisible architecture, the cosmic web, upon which the visible universe of galaxies is built and arranged. Despite all this compelling indirect evidence for its existence and its profound gravitational effects, the actual fundamental nature and composition of dark matter remain one of the greatest unsolved mysteries in all of modern physics. What is this elusive stuff made of? Is it composed of some exotic, undiscovered type of fundamental particle that interacts only very weakly with ordinary matter and light? Perhaps WIMPs, weakly interacting massive particles, or perhaps axions, another hypothetical particle. These particles would have been created in the hot early universe and would now drift through space, largely unseen and unfelt, except through their collective gravity. Or could dark matter be something even more strange and unexpected, like primordial black holes formed in the extreme conditions of the very early universe, before stars existed? Or perhaps some other, even more exotic form of matter that our current theories of particle physics don't yet account for? Scientists around the world are currently engaged in a multi-pronged, intensive effort to try and detect dark matter particles, directly or indirectly. These experiments include direct detection experiments. These are often located deep underground, in specially shielded laboratories to minimize interference from cosmic rays and other background radiation, using highly sensitive detectors made of materials like liquid xenon, germanium crystals, or supercooled silicon. The hope is that a rare WIMP or other dark matter particle, so far, despite increasing sensitivity, these experiments have yielded no definitive, unambiguous detection of dark matter particles, though they have placed increasingly stringent limits on their possible properties. In direct detection experiments, these search for the products of dark matter particle annihilation or decay. If dark matter particles can collide and annihilate each other, or if they are unstable and decay, they might produce a faint but detectable signal of ordinary particles, like gamma rays, neutrinos, or antimatter particles, coming from regions where dark matter is expected to be concentrated, such as the center of our Milky Way galaxy or nearby dwarf galaxies. In direct camera experiments, the center of our Milky Way galaxy or nearby dwarf galaxy telescopes like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station are actively searching for such signals. Collider experiments. High-energy particle accelerators like the Large Hadron Collider, LHC, at CERN could potentially create dark matter particles in energetic collisions of ordinary particles. If dark matter particles are produced, they would escape the detectors without interacting, but their presence could be inferred by looking for missing energy and momentum in the collision products. As you lie back and allow your mind to wander through the vast, silent, star-strewn expanse of space, imagine this immense, unseen web of dark matter stretching invisibly throughout the entire universe, silently guiding the formation and evolution of all the galaxies and stars we can perceive. It's a profound and humbling reminder that even in the most well-explored domains of science, there are still deep, fundamental mysteries lurking just beyond our current sight, waiting to be unveiled. Dark matter challenges our most basic understanding of the material composition of the cosmos, urging us to look beyond the visible, to question the completeness of our current theories, and to ponder the true nature of reality itself. In the quiet solitude of the night, as you drift off to sleep, let the profound mystery of dark matter envelop you, an invisible, omnipresent, yet overwhelmingly influential force, silently shaping your dreams and guiding the grand, cosmic dance across the silent, star-hilled universe. Dark energy. Imagine, once more, that you are holding an uninflated balloon in your hands. As you begin to steadily blow air into it, you watch it expand, its surface stretching outwards in all directions, the dots you might have drawn on it moving farther and farther apart. Now picture this balloon not just as a simple toy, but as a metaphor for our entire universe. Just as the balloon grows larger with each breath, so too does our universe, its vast fabric of space expanding ever outward over the eons. But here's where the analogy takes an unexpected, even startling twist. Imagine that after an initial period of steady inflation, the rate at which the balloon is expanding suddenly begins to increase. It's as if an unseen, mysterious force is now pumping even more air into the balloon, causing it to swell faster and faster as time goes on, pushing those dots apart with ever-increasing velocity. This mysterious, pervasive agent, this unseen pressure that appears to be driving the accelerating expansion of our universe, is what scientists have dubbed, with a fitting sense of its enigmatic nature, dark energy. Dark energy is without a doubt one of the most baffling, profound, and consequential concepts in all of modern cosmology. If its equally mysterious cousin, dark matter, acts like an invisible cosmic scaffold, its pervasive gravity helping to hold galaxies and clusters of galaxies together, then dark energy is something altogether different. It acts more like an omnipresent cosmic wind, or an inherent springiness to space itself that is actively pushing everything apart on the largest scales. It's a deeply counterintuitive notion. While gravity, the fundamental force we intuitively expect to dominate the large-scale dynamics of the universe, should be attractive, pulling all matter together and thus gradually slowing down the cosmic expansion over time, dark energy appears to be working in precisely the opposite direction, overwhelming gravity on cosmic scales and causing galaxies to recede from each other at an ever-increasing accelerating speed. The discovery of this cosmic acceleration, and thus the inference of dark energy's existence in the late 1990s, sent profound shockwaves rippling through the entire scientific community. It was a discovery that fundamentally altered our understanding of the universe's composition, its past evolution, and its ultimate destiny, based on a convergence of evidence from multiple independent cosmological observations, including the precise measurements of distant Type Ia supernovae, the detailed analysis of the cosmic microwave background radiation, and studies of the large-scale distribution of galaxies. Astronomers and physicists have come to a startling conclusion. Dark energy is estimated to constitute about 68% to 70% of the entire universe. This means that the vast majority, more than 2/3 of what comprises the cosmos, is this utterly mysterious, invisible, and gravitationally repulsive substance or phenomenon that we cannot yet see, cannot touch, and cannot fully comprehend with our current physical theories. Ordinary matter, the stuff of stars, planets, and ourselves, makes up a mere 5% of the universe, with dark matter accounting for the remaining 25–27%. The story of dark energy's discovery is a fascinating chapter in modern science. In the late 1990s, two independent international teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, co-led by Brian Schmidt and Adam. These colossal stellar explosions, resulting from the thermonuclear detonation of white dwarf stars that have accreted too much mass from a binary companion, are incredibly bright and, crucially, they all explode with a remarkably consistent intrinsic brightness. This makes them excellent standard candles for measuring vast cosmic distances. By precisely measuring the apparent brightness and redshift of these distant supernovae, the astronomers aimed to determine how the expansion rate of the universe had changed over cosmic time. Most cosmologists at the time expected to find that the expansion was slowing down due to the mutual gravitational attraction of all the matter in the universe. However, both teams, independently and using different data sets, found something astonishing and completely unexpected. The distant supernovae were consistently dimmer and therefore farther away than they should have been if the universe's expansion was decelerating or even constant. The only way to explain these observations was if the expansion of the universe had actually been speeding up over the past 5 to 6 billion years. This was a revolutionary finding, the opposite of what almost everyone had anticipated. It implied the existence of some unknown, gravitationally repulsive force or energy pervading space, which was overcoming the attractive pull of gravity on cosmic scales and driving this acceleration. This unknown agent was quickly dubbed dark energy. For this groundbreaking discovery, Perlmutter, Schmidt and Rees were awarded the Nobel Prize in Physics in 2011. To get a more intuitive sense of how strange and counterintuitive this is, imagine throwing a ball high up into the air. Normally, you would expect Earth's gravity to steadily slow the ball's ascent, eventually stop it, and then pull it back down. But what if, instead of slowing down, the ball suddenly began to speed up as it rose, accelerating faster and faster, flying off into the sky with ever-increasing velocity, as if some invisible, repulsive force from the Earth itself was pushing it away with increasing strength? That's essentially what dark energy appears to be doing to the galaxies in our universe on the largest scales. Instead of being reined in and eventually pulled back together by their mutual gravity, distant galaxy clusters are being pushed apart by this enigmatic, all-pervading dark energy. Dark energy isn't just a minor player in the cosmic drama. It is the dominant component of the universe's energy budget today, and its influence is growing. One of the most peculiar and defining characteristics of dark energy, at least in its simplest theoretical form, the cosmological constant model, is that its energy density appears to remain constant, or nearly constant, as the universe expands. This is very different from ordinary matter, or dark matter, whose energy density decreases as the universe expands, because the same amount of matter is spread out over a larger volume. If dark energy's density remains constant, then as space expands, the total amount of dark energy in any given expanding volume actually increases. This means that as the universe gets bigger, dark energy becomes increasingly dominant over matter and radiation, leading to the observed acceleration. It's as if the more the universe expands, the more room there is for dark energy, which then fuels the expansion even further. This creates a kind of runaway feedback loop, where the expansion of space generates or reveals more dark energy, which in turn accelerates the expansion even more. One of the most profound and pressing questions in all of fundamental physics and cosmology today is, what is the true nature of dark energy? There are several leading theoretical ideas, but as yet no definitive answers and no direct experimental detection. The cosmological constant, vacuum energy, perhaps the simplest and currently most favored explanation. It proposes that dark energy is an intrinsic, fundamental energy density of empty space itself, a vacuum energy predicted by quantum field theory, but with a magnitude that is vastly smaller by an almost incomprehensible factor of 10, except 120 subsets, than simple theoretical calculations would suggest. This idea harks back to Einstein's cosmological constant, lambda L, which he introduced into his equations of general relativity to allow for a static universe, and later discarded as his biggest blunder when the universe was found to be expanding. Ironically, a non-nano cosmological constant with a very small positive value, now seems to be the best fit to the observational data for dark energy. Why its value is so small, yet non-nano, is one of the deepest mysteries in physics, often called the cosmological constant problem and the coincidence problem. Why dark energy is becoming dominant only relatively recently in cosmic history. Quintessence. Dynamical dark energy, that proposes that dark energy is not constant, but is instead associated with a new dynamic ultralight scalar field, similar in some ways to the inflaton field, hypothesized to have driven cosmic inflation in the very early universe, that pervades all of space and evolves slowly over cosmic time. The energy density of this quintessence field could change as the universe expands, potentially leading to different future scenarios for the cosmos than the cosmological constant model. Modified gravity. Some theories suggest that dark energy might not be a new substance or field at all, but rather an indication that Einstein's theory of general relativity itself needs to be modified on very large cosmological scales. Perhaps gravity behaves differently over vast distances than it does in our solar system or within galaxies, leading to an apparent cosmic acceleration without the need for a separate dark energy component. As strange, elusive, and deeply mysterious as dark energy is, its implications for the ultimate fate of the universe are even more profound and somewhat unsettling. If dark energy continues to dominate the universe, and its repulsive effect remains constant or strengthens, as in some phantom energy models, then the future of the cosmos could be rather bleak and lonely. In the far, far distant future, many billions or even trillions of years from now, the universe will likely continue its accelerating expansion. Galaxies will recede from each other ever faster, eventually being carried beyond our cosmic event horizon, disappearing from our view one by one. The stars within our own local group, which will eventually merge into a single giant galaxy, Mokomoda, will exhaust their fuel and die out. The universe will drift into a state of eternal accelerating expansion, becoming increasingly cold, dark, dilute, and empty. This scenario is sometimes known as the Big Freeze, or the heat death of the universe, where all structure eventually dissolves and all activity ceases. In more extreme and highly speculative Big Rip scenarios, if dark energy's repulsive force grows stronger over time, it could eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. So, as you lie back and allow your thoughts to drift into the silent, vast, and star-strewn expanse of space, consider the profound enigma of dark energy. It is a powerful and humbling reminder that despite all our accumulated knowledge and incredible scientific progress, there are still deep, fundamental mysteries lurking in the cosmos. Mysteries that challenge our most basic understanding of reality itself. Dark energy is the invisible, yet dominant, hand shaping the universal's ultimate destiny, a force that defies our everyday intuition and pushes the boundaries of our comprehension. As you drift off to sleep, let the thought of this mysterious, pervasive, and accelerating force guide your dreams, expanding your imagination just as it relentlessly expands the universe, pushing the boundaries of what we know, what we can conceive, and what we have yet to discover in this magnificent, enigmatic, and ever-evolving cosmos. Supernova. Picture in the vast theatre of the night sky a star. Not just any star, but a colossal, incandescent sphere of superheated gas, suspended in the cold vacuum of space, perhaps many times more massive than our own sun. For millions, sometimes even hundreds of millions of years, this stellar giant maintains a delicate, self-regulating equilibrium, a cosmic balancing act. Deep within its core, a furious nuclear furnace rages, transmuting lighter elements into heavier ones, primarily hydrogen into helium, releasing a prodigious amount of energy in the form of light and heat. This outward radiation pressure, generated by the nuclear fusion, perfectly counteracts the relentless inward crush of the star's own immense gravity, keeping it stable and shining brightly. But for some stars, particularly these massive ones, there inevitably comes a critical juncture when this intricate balance falters, when the nuclear fuel in the core begins to run out. The star can no longer sustain its outward pressure against the overwhelming force of gravity in its final, dramatic and breathtaking moments. It undergoes one of the most violent, energetic, and visually spectacular events in the entire universe, a supernova. A supernova is not merely the quiet death of a star, it is a cataclysmic, cosmic explosion of almost unimaginable power and brilliance, a pyrotechnic display on a truly galactic scale. For a brief period, typically lasting a few weeks or months, the light from a single supernova can outshine its entire host galaxy, which itself may contain hundreds of billions of other stars. In fact, if a supernova were to occur relatively close to Earth, within our own Milky Way galaxy for instance, though thankfully such events are rare and none have been close enough to be dangerous in recorded history, it could become easily visible in the night sky, even to the unaided eye, potentially even shining brightly enough to be seen during the daytime. These guest stars, as they were sometimes called by ancient astronomers, have been recorded throughout history, their sudden appearance a source of awe and wonder. But what astrophysical processes trigger such a monumentally powerful event? To understand a supernova, it's helpful to continue thinking of a star as a vast, self-contained nuclear reactor. Deep within its core, under conditions of extreme temperature and pressure, nuclear fusion reactions convert lighter elements into heavier ones. For most of a star's life, the primary fusion process is the conversion of hydrogen into helium. This process releases a tremendous amount of energy, which creates an outward thermal and radiation pressure that supports the star against gravitational collapse. However, as the star ages and consumes more and more of its nuclear fuel, this delicate balance begins to unravel. When a truly massive star, one with an initial mass typically greater than about 8 to 10 times that of our Sun, reaches the end of its life, it has exhausted the hydrogen in its core. It then begins to fuse helium into carbon and oxygen. This process continues, with the core contracting and heating up, igniting successive stages of fusion involving heavier and heavier elements, forming concentric shells within the star, much like the layers of an onion. Carbon fuses into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally silicon into iron. But iron is a critical turning point. The fusion of iron nuclei and elements heavier than iron does not release energy, instead it absorbs energy from its surroundings. So when the core of the massive star becomes predominantly composed of iron, it has effectively reached a nuclear dead end. There is no further energy generation possible from fusion in the core to counteract the relentless inward pull of gravity. At this point, the iron core, which might be about the size of the Earth but contain more mass than our Sun, becomes catastrophically unstable. In a mere fraction of a second, with no outward pressure to support it, the iron core collapses in on itself under its own tremendous weight. It shrinks with incredible speed, from a size comparable to a planet down to a diameter of only a few tens of kilometers. This rapid, violent implosion heats the core to billions of degrees Celsius and compresses it to unimaginable density. The collapse is so sudden and violent that the inner part of the core overshoots its equilibrium point and then bounces back, triggering an enormously powerful shock wave. This shock wave, further energized by a massive burst of neutrinos released from the collapsing core, blasts outward through the star's overlying layers of gas, tearing the entire star apart in a colossal runaway explosion. This is a Type II supernova, or sometimes Type IB or ICI, depending on whether the star had previously lost its outer hydrogen or helium layers. The outer layers of the star, containing many solar masses of material, are violently ejected into interstellar space at speeds that can reach up to 10% of the speed of light. Meanwhile, the incredibly dense core remnant is typically compressed into either a neutron star, an ultra-dense ball of neutrons, as discussed previously, or if the original star was exceptionally massive, perhaps more than 20-25 times the Sun's mass, its gravity might be so overwhelming that even the neutron degeneracy pressure cannot halt the collapse, and it continues to implode, forming a black hole. The energy released in a supernova explosion is so immense that it beggars description. A single supernova can release more energy in just a few seconds than our Sun will produce over its entire 10 billion year lifespan. This explosion also hurls vast quantities of enriched material, the star's processed elements, into the interstellar medium. This ejected material includes not only the lighter elements like hydrogen, helium, carbon and oxygen from the star's outer layers, but also a host of heavier elements, including many of those essential for life, such as calcium, silicon, sulfur, and, crucially, elements heavier than iron, like gold, silver, platinum, lead, and uranium. These very heavy elements are forged primarily in the extreme conditions of the supernova explosion itself, through rapid neutron capture processes, the R process that occur in the intense heat, pressure, and neutron flux of the exploding material. This stellar debris, now rich in a diverse array of newly synthesized chemical elements, is scattered far and wide across the cosmos, eventually mixing with existing interstellar gas and dust clouds. These enriched clouds then become the raw material, the building blocks, for new generations of stars, new planetary systems, and ultimately the very possibility of life as we know it. In a very real and beautiful sense, every atom of gold in your jewelry, every bit of iron in your blood, every molecule of calcium in your bones, every trace of silicon in the rocks beneath your feet, was once forged in the heart of a dying, exploding star, or, in the even more exotic collisions of neutron stars, which are also a significant source of R process elements. Supernovae are therefore absolutely vital to the chemical evolution of the universe and the emergence of life. They play a key, indispensable role in dispersing these heavy, life-critical elements throughout galaxies. Without supernovae, the universe would be a much simpler, more chemically barren place, composed almost entirely of the primordial elements created in the Big Bang, hydrogen and helium, with trace amounts of lithium. The explosive deaths of massive stars enrich the interstellar medium, the diffuse gas and dust between stars, with the diverse palette of chemical elements necessary to form complex structures like rocky planets, habitable moons, and, crucially, the complex organic molecules that are the basis of living organisms. In this sense, supernovae are not just an end, a destructive event. They are also a profound beginning, a kind of cosmic recycling program and enrichment process that makes new creation, new complexity, and new life possible. It's also worth noting that not all supernovae are of this core-centric Type II variety. There is another major class, known as Type Ia supernovae. These typically occur in binary star systems, where one of the stars is a white dwarf, the dense, Earth-sized remnant of a Sun-like star that has exhausted its nuclear fuel. If this white dwarf is in a close orbit with a companion star, either a main sequence star or a red giant, it can gravitationally accrete material, hydrogen and helium, from its companion. Over time, if the white dwarf accumulates enough mass from its companion, approaching a critical limit known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun, the pressure and temperature in its degenerate carbon-oxygen core can become high enough to ignite runaway nuclear fusion of carbon and oxygen. This triggers a cataclysmic thermonuclear detonation that completely obliterates the white dwarf in a brilliant, standardized Type A supernova explosion. Because these explosions are thought to occur when the white dwarf reaches a very specific, well-defined mass, they all have a remarkably consistent peak luminosity, intrinsic brightness. This makes Type Ia supernovae incredibly valuable tools for astronomers, serving as standard candles to measure vast cosmic distances and to probe the expansion history of the universe. It was observations of distant Type O supernovae that led to the discovery of dark energy and the accelerating expansion of the universe. One of the most famous and well-studied supernovae in recent history is supernova 1987A, which exploded in the Large Magellanic Cloud, a small satellite galaxy of our Milky Way, about 168,000 light-years away. Its light reached Earth in February 1987, making it the closest supernova to Earth observed in over 400 years, since Kepler's supernova in 1604. SN 1987A was a Type II supernova, resulting from the core collapse of a blue supergiant star. Its relative proximity provided astronomers with an unprecedented, once-in-a-lifetime opportunity to study a supernova up close and in great detail across the entire electromagnetic spectrum, and even to detect neutrinos from the collapsing core, which arrived a few hours before the light, confirming theoretical models of core collapse. Observations of SN 1987A and its expanding remnant over the subsequent decades have yielded invaluable insights into the complex physics of supernova explosions, the formation of heavy elements, and the evolution of supernova remnants. As you drift off to sleep, think of the countless stars twinkling silently in the night sky. Each one is a massive, incandescent ball of gas, burning brightly in the dark, cold expanse of space. Some of them are quietly living out their long, stable lives, fusing hydrogen into helium for billions of years, much like our own sun. But others, the cosmic giants, the massive stars, are destined for a much more dramatic and spectacular end. An end that is also a new beginning. They are poised, at some unknown future moment, to go out in a brilliant, cataclysmic blaze of glory. A supernova that will briefly outshine their entire galaxy and seed the cosmos with the precious elements of creation. These cosmic fireworks are a profound and beautiful reminder that even in death, even in destruction on the grandest imaginable scale, there is renewal, there is creation, there is the potential for new life. The universe is in a constant dynamic state of flux, with stars being born from cosmic nurseries, living out their lives, and then, in their final dramatic act, giving back their enriched material to the cosmos, paving the way for future generations of stars, planets, and perhaps light. Supernovae are the ultimate paradox of destruction and creation. A brilliant, fleeting, yet profoundly influential moment that shapes the very fabric, the chemical composition, and the ultimate destiny of the universe. Pulsars. Imagine yourself once again standing on a desolate, otherworldly shoreline, gazing out into an infinite, inky black ocean that is the vastness of interstellar space. In the far, unfathomable distance, a solitary, incredibly powerful lighthouse pierces the profound darkness. Its brilliant, focused beam of light, or rather a beam of intense electromagnetic radiation, sweeps across the cosmic horizon with an unwavering, almost perfect clockwork regularity. This celestial beacon is not guiding ships through treacherous terrestrial waters, but rather it is sending its rhythmic signals across the light years, a cosmic metronome marking time in the silent emptiness of the galaxy. This is the essence, the poetic image of a pulsar, a cosmic lighthouse, a natural wonder forged by the extreme physics of stellar death. Pulsars are a special, highly magnetized, and extraordinarily rapidly rotating type of neutron star, and neutron stars themselves, as we've touched upon, are the incredibly dense, compact remnants left behind after a massive star, one significantly more massive than our Sun, undergo a cataclysmic supernova explosion at the end of its life. When such a star exhausts its nuclear fuel, its core can no longer support itself against the crushing force of its own gravity and collapses catastrophically. If the mass of this collapsing core is within a certain range, typically between about 1.4 and perhaps 2 to 3 times the mass of our Sun, it doesn't become a black hole, but instead forms an ultra-dense object called a neutron star, a sphere perhaps only about 20 kilometers, roughly 12 miles, in diameter, yet containing more mass than our entire Sun. But pulsars are not just any neutron stars. They possess a unique and defining characteristic that makes them detectable and so fascinating. They emit powerful, highly focused beams of electromagnetic radiation from their magnetic poles. These beams are generated by complex processes involving the neutron star's incredibly strong magnetic field and its rapid rotation. The radiation in these beams can span a wide range of the electromagnetic spectrum, from radio waves, which is how most pulsars are initially detected, to visible light, X-rays, and even extremely energetic gamma rays. These beams are so intense that, if they happen to sweep across the Earth as the pulsar rotates, they can be detected by our telescopes, appearing as regular, repeating pulses of energy. What makes pulsars particularly captivating, and indeed useful to astronomers, is their astonishing rotational speed and the remarkable precision of their pulses. As the original massive progenitor star collapses from a vast size, many millions of kilometers in diameter, down to the tiny size of a neutron star, it conserves its angular momentum. This is the same physical principle that causes a spinning ice skater to spin much faster when they pull their arms in close to their body. The dramatic reduction in size during the supernova collapse results in the newly formed neutron star spinning at incredibly high velocities. Many pulsars rotate several times per second, and some, particularly a class known as millisecond pulsars, which are often found in binary systems and are thought to have been spun up by accreting matter from their companion star, can rotate hundreds or even over 1,000 times per second. Imagine an object more massive than the Sun, crushed into the size of a city, spinning faster than a kitchen blender. As these pulsars spin, their immensely powerful magnetic fields, which can be trillions of times stronger than Earth's magnetic field, and are also frozen in and amplified during the collapse, accelerate charged particles, electrons, near the star's surface to nearly the speed of light. These accelerated particles then emit radiation in tight conical beams along the magnetic field lines, primarily through processes like synchrotron radiation, when charged particles spiral in a magnetic field, and curvature radiation, when charged particles move along curved magnetic field lines. If the pulsar's magnetic axis is not perfectly aligned with its rotational axis, which is usually the case, much like Earth's magnetic poles are offset from its geographic poles, then these lighthouse-like beams will sweep across space as the neutron star rotates. When one of these beams happens to sweep across the Earth, our radio telescopes, or X-ray or gamma-ray telescopes depending on the pulsar, detect a brief, sharp pulse of energy. This happens once, or sometimes twice if both beams sweep past us, per rotation of the pulsar. The precision of these pulses is truly astounding, especially for millisecond pulsars. They are some of the most accurate natural clocks in the entire universe. Their rotational periods are incredibly stable, changing only very, very gradually over long timescales. As the pulsar slowly loses rotational energy, in fact, the stability of certain pulsars rivals and in some cases even surpass that of the best atomic clocks on Earth. This remarkable regularity makes pulsars invaluable tools for a variety of astrophysical experiments. For example, arrays of precisely timed millisecond pulsars, forming a pulsar timing array, are being used to try and detect the subtle nanohertz frequency gravitational waves produced by pairs of merging supermassive black holes at the centers of distant galaxies. These gravitational waves would cause tiny, correlated shifts in the arrival times of the pulsar signals from different directions in the sky. Pulsars are also used to test Einstein's theory of general relativity in strong gravitational fields, especially binary pulsars, where two neutron stars orbit each other to map the distribution of free electrons in the interstellar medium. By observing how pulsar signals are dispersed as they travel through it, and even to aid in spacecraft navigation in deep space, X-ray pulsar-based navigation, or XNAV. The discovery of pulsars was one of the most exciting and serendipitous astronomical breakthroughs of the 20th century, and it has a wonderful story. In 1967, Jocelyn Bell Burnell, then a graduate research student at the University of Cambridge, was meticulously analyzing chart recorder data from a newly constructed radio telescope array that she had helped build. She noticed a strange, repeating series of brief radio pulses, a bit of scruff coming from a fixed point in the sky. These pulses were remarkably regular, occurring every 1.337 seconds. They were so precise and regular, in fact, that at first she and her PhD supervisor, Anthony Hewish, half-jokingly considered the possibility that they might be artificial signals from an extraterrestrial civilization. They even provisionally labeled the source LGM-1. However, it soon became clear, as Bell Burnell discovered more such pulsating sources from different parts of the sky, that these signals were not from aliens, but were from a previously unknown, natural type of rapidly rotating magnetized neutron star, what we now call a pulsar. Anthony Hewish later received the Nobel Prize in Physics in 1974 for his decisive role in the discovery of pulsars. Jocelyn Bell Burnell's non-inclusion has been a subject of considerable debate and controversy ever since, though she has received many other prestigious awards for her pivotal role. One of the most famous and well-studied pulsars is the Crab pulsar, PSR B 531 plus 21, located at the very heart of the Crab Nebula, a spectacular and well-known supernova remnant in the constellation Taurus, about 6,500 light-years from Earth. The Crab Nebula is the gaseous remnant of a supernova explosion that was observed and recorded by Chinese and other astronomers in the year 1054. The Crab pulsar, the neutron star left behind by that explosion, rotates incredibly rapidly, about 30 times per second. Its period is 33 milliseconds, and its energetic beams of radiation can be detected across the entire electromagnetic spectrum, from radio waves all the way up to very high-energy gamma rays. The Crab pulsar is a vivid and dynamic reminder of the violent death of a massive star and the exotic, energetic object it can leave behind, its regular, rapid pulses serving as a kind of cosmic metronome, steadily ticking away in the vast, silent expanse of space. Pulsars come in a variety of different types and flavors, depending on their age, rotational speed, magnetic field strength, and the type of radiation they predominantly emit. Besides the normal radio pulsars, which make up the majority of known pulsars, and the incredibly fast millisecond pulsars, there are also X-ray pulsars, often in binary systems where matter from a companion star is accreting onto the neutron star's magnetic poles. Gamma-ray pulsars, whose beams are primarily detected at gamma-ray energies, and the aforementioned magnetars, a rare type of neutron star with magnetic fields that are even more extraordinarily intense, thousands of times stronger than typical pulsars, leading to violent bursts of X-rays and gamma rays. These different types of pulsars showcase the incredible diversity of these cosmic lighthouses and the extreme, often bizarre, physics that governs their behavior. Beyond their role as precise cosmic clocks and fascinating astronomical objects in their own right, pulsars also provide invaluable insights into the fundamental nature of matter and the forces that govern the universe under the most extreme conditions imaginable. Because they are so incredibly dense, a teaspoonful would weigh billions of tons. Pulsars allow scientists to study the behavior of matter under conditions of pressure and density that are utterly impossible to replicate in any terrestrial laboratory. The interior of a pulsar is a realm of truly exotic physics, with theories suggesting it might be composed of a superfluid of neutrons, perhaps with a core of even more exotic forms of matter like a quark-gluon plasma, where protons and neutrons themselves break down into their constituent quarks and gluons, or strange matter, a hypothetical form of quark matter containing strange quarks in addition to up and down pulsars, with their precisely timed pulsars and their existence in the most extreme physical environments, serve as natural laboratories for testing the very limits of our understanding of physics. They challenge our theories of gravity, nuclear physics, and plasma astrophysics, and they offer tantalizing glimpses into the violent, dynamic, and often counterintuitive processes that shape the cosmos. As you close your eyes and prepare to drift off to sleep, imagine the steady, rhythmic pulse of a distant pulsar, spinning relentlessly and faithfully in the vast, cold darkness of interstellar space. Like a tiny, powerful cosmic heartbeat, its signal, born of unimaginable density and energy, travels across the light years, a silent yet profound reminder of the strange, beautiful, and often extreme universe that surrounds us. These cosmic lighthouses, though unimaginably far away, connect us directly to the deepest mysteries of the stars, the fundamental nature of matter, and the unimaginable forces that govern our existence. The observable universe. Imagine yourself standing on the very edge of an immense, boundless ocean, its waters stretching out to a distant, hazy horizon. You can see the waves rolling in towards the shore. You can feel the mist on your face, and you can perhaps discern some distant islands or ships near that visible limit. But you know, with absolute certainty, that the ocean continues far, far beyond what your eyes can perceive, far beyond that tangible horizon line. The true, full expanse of this global ocean is vastly larger than the portion you can see from your single vantage point. This is a very apt analogy for our view of the cosmos. What we can actually see, measure, and study with our telescopes and instruments is confined to what we call the observable universe. This is, in essence, a finite spherical bubble within a potentially infinite, or at least vastly, unimaginably larger, total universe. It is the portion of the cosmos from which light, or any other form of information limited by the cosmic speed limit, the speed of light, has had sufficient time to reach us since the very beginning of the universe, approximately 13.8 billion years ago. The observable universe therefore represents the patch of the cosmic ocean that is, in principle, accessible to our observations. It's like that visible sweep of ocean out to the horizon, tangible to our senses or our scientific instruments, measurable in its properties, yet almost certainly only a tiny localized fraction of the entire true cosmic sea. The distance that light has traveled to reach us from the very edge of this observable region, from the most distant objects we can currently detect, is, naturally, about 13.8 billion light-years. However, a crucial point to understand is that because the universe itself has been expanding continuously during the entire time that this ancient light has been journeying towards us, the objects that emitted that light are now much, much farther away from us than they were when the light began its voyage. Current cosmological models, taking into account this cosmic expansion, estimate that the actual radius of the observable universe today is approximately 46.5 billion light-years in every direction from us. This gives our observable cosmic bubble a staggering diameter of roughly 93 billion light-years. To try and put this almost incomprehensible scale into some kind of human perspective is a daunting task. Imagine for a moment that a single grain of fine sand represents our entire Milky Way galaxy, with its hundreds of billions of stars, its vast clouds of gas and dust, and its retinue of planets. If our galaxy is just one grain of sand, then the observable universe, on this scale, would be a colossal sphere, perhaps the size of a large building or even a small town, absolutely packed to the brim with such grains of sand. Current estimates suggest that our observable universe contains something on the order of 2 trillion galaxies, each one a vast, gravitationally bound island universe, containing anywhere from millions to trillions of its own stars, along with countless planets, nebulae, black holes, and other celestial wonders. Yet, despite these mind-boggling, almost dizzying numbers, this observable section of the cosmos, this cosmic bubble that we inhabit and can probe, is, in all likelihood, just an infinitesimal speck, a minuscule drop within an unimaginably larger, perhaps even infinitely vast, total cosmic ocean. What lies beyond our current observational horizon? What is the nature of the universe beyond the edge of what we can, even in principle, ever see? That remains one of the most tantalizing, profound, and perhaps ultimately unanswerable questions in all of modern cosmology. Our view of the universe is fundamentally, irrevocably constrained by the finite speed of light, which acts as the ultimate cosmic speed limit for the transmission of any information. Even if there are countless trillions more galaxies, unimaginable superstructures, and perhaps even entirely different cosmic domains existing beyond the current boundary of our observable universe, their light simply hasn't had enough time to reach us since the universe began its expansion some 13.8 billion years ago. It's like standing in the very heart of an infinitely dense, primeval forest, able to see only the trees that are immediately surrounding you, while the rest of the boundless, unexplored wilderness remains forever shrouded in an impenetrable gloom of immense distance and vast, unbridgeable time. But what about those distant, almost mythical edges of our observable universe? A fascinating and crucial consequence of the finite speed of light is that as we peer farther and farther out into space with our powerful telescopes, we are also, simultaneously and unavoidably, looking further and further back in time. The light from a galaxy that we observe to be, say, 10 billion light-years away from us began its immense journey towards our telescopes 10 billion years ago. So when we capture that ancient light and form an image of that distant galaxy, we are not seeing it as it exists today, in its current state of evolution. Instead, we are seeing it as it was 10 billion years in the past, when the universe itself was much younger, only about 3.8 billion years old. This means that the observable universe is not just a spatial snapshot of what exists out there right now, it is also, profoundly, a temporal window into the deep history of the cosmos itself, a kind of living, evolving, four-dimensional record of the universe's maturation and development over eons. The most distant light we can currently detect is not from individual galaxies, but is the cosmic microwave background, CMB radiation, the faint, pervasive afterglow of the Big Bang itself. This ancient light comes to us from a time when the universe was only about 380,000 years old, long before the first stars and galaxies had even formed. The CMB effectively marks the boundary of our visible universe, the surface of last scattering beyond which the early universe was opaque to light. Now, let's ponder for a moment the profound implications of this vast, yet ultimately limited view of our cosmic home. Even if we could somehow construct a spacecraft capable of traveling at the speed of light, which is physically impossible for any object with mass according to Einstein's theory of special relativity, it would still take us an unimaginable 13.8 billion years to reach the current light travel time edge of our observable universe. And yet, despite this almost incomprehensible immensity, the observable universe is, in all probability, only a tiny, perhaps infinitesimal, fraction of the entire cosmos. Some cosmological theories, particularly those that incorporate a period of incredibly rapid expansion, suggest that the total universe, beyond our observable bubble, could be vastly, vastly larger, perhaps many orders of magnitude larger, or even truly geometrically infinite in spatial extent. In such a scenario, our entire observable universe, with its trillions of galaxies, would be akin to a single atom within an infinite, boundless ocean. Other, more complex cosmological models propose that the universe might have a finite but much larger, and perhaps even a non-trivial, complex topology, like a multi-dimensional torus or donut shape, for example, but still far more extensive than we can ever hope to directly perceive or map. One of the most mind-bending aspects related to the concept of the observable universe arises from the fact that our universe is not static, but is continuously expanding. And not just expanding, but its expansion is accelerating, driven by the mysterious force of dark energy. As space itself stretches at an ever-increasing rate, the distances between gravitationally unbound galaxy clusters are growing larger and larger. A very distant galaxy, that is, currently just within our observable horizon, is receding from us at a speed approaching, and, due to the expansion of space itself, can even exceed the speed of light. As this accelerating expansion continues, galaxies that are currently visible to us but are very far away will eventually be carried away so fast that their light will no longer be able to reach us, no matter how long we wait. They will, in effect, cross over our cosmic event horizon and disappear from our view forever. their light redshifted into oblivion. This leads to a rather unsettling and perhaps counterintuitive thought. While the physical size of the region from which light could have reached us since the Big Bang, the observable universe, continues to grow as time passes, simply because more time has elapsed, the actual number of individual galaxies that we will be able to see in the very far distant future will actually decrease. The inventory of observable cosmic structures will shrink over cosmic timescale. Our accessible universe, in terms of the objects it contains that will remain within observational reach, is, in a profound sense, diminishing over the vast sweep of future cosmic time. So here we stand, metaphorically, on the fragile shores of an unimaginably vast cosmic ocean, gazing out at the ancient waves of light that we can perceive, knowing with a deep sense of both wonder and humility that there is so much more beyond our current horizon, so much that may forever remain beyond our direct grasp. The observable universe is a profound and beautiful testament to both the incredible, almost miraculous reach of our scientific inquiry and the inherent fundamental limitations imposed upon us by the very laws of nature and the history of the cosmos. It is a tiny, brilliantly illuminated patch of reality within a much grander, darker, and possibly forever hidden from our direct view. As you drift off to sleep tonight, let the sheer, mind-stretching vastness of this concept wash over you like a gentle cosmic tide. Let it remind you that even within the immense cosmic bubble that we can perceive, with its trillions of galaxies and its billions of years of history, there is still so much to discover, so much to understand, so much beauty to behold, and so much profound wonder to fuel our imaginations and our relentless quest for knowledge. For as long as our species endures on this small, precious world, Fermi paradox, in our persistent, deeply human quest to comprehend our place within the vast, star-strewn tapestry of the universe, and to answer that most ancient and resonant of questions, are we alone? The Fermi paradox stands as one of the most profound, intellectually stimulating, and deeply perplexing enigmas in all of modern science and philosophical thought. Named after the brilliant Italian-American physicist Enrico Fermi, who is said to have famously and perhaps apocryphally posed the core question during a casual lunchtime conversation with colleagues at Los Alamos National Laboratory in the summer of 1950. But where is everybody? The paradox emerges from a stark, seemingly irreconcilable and deeply unsettling contrast, given the sheer, almost unimaginable number of stars and potentially habitable planets that are now known to exist within our Milky Way galaxy alone, and given the immense age of the universe, which should have provided ample time for life to arise and evolve elsewhere, why have we not yet detected any unambiguous, verifiable, or widely accepted signs of extraterrestrial civilizations? To truly explore the depths of this paradox is to delve into the vastness of the cosmos, to contemplate the probabilities of life's emergence and evolution, to consider the potential trajectories of technological civilizations, and to confront the myriad of speculative and often unsettling possibilities that could explain this profound, great silence from the stars. Picture, if you will, our Milky Way galaxy not just as a beautiful, swirling collection of stars visible on a dark night, but as a colossal, bustling, star-studded cosmic metropolis, This galactic city contains hundreds of billions of individual residences, stars, and we now know, thanks to modern astronomical surveys like the Kepler Space Telescope and TESS, Transiting Exoplanet Survey Satellite, that a very large fraction of these stars are likely to host planetary systems. Many of these planets, perhaps tens of billions in our galaxy alone, are expected to be roughly Earth-sized and to reside within their star's habitable zone, the orbital region where temperatures could allow liquid water, a key ingredient for life as we know it, to exist on the planet's surface. Within this unimaginably vast cosmic city, with its countless potential abodes for life, the statistical possibilities for the independent emergence of life, and eventually the evolution of intelligent life and technologically advanced civilizations, seem nearly endless, almost overwhelming. If we assume, even with a degree of scientific conservatism, that the processes that led to life and intelligence on Earth are not unique, that they are natural, albeit perhaps complex, outcomes of universal physics and chemistry, given enough time and suitable environmental conditions, then we might reasonably expect to encounter numerous signs of other civilizations' existence, and the signs of These signs could manifest in various ways, perhaps through deliberate attempts at interstellar communication, e.g., powerful patterned radio signals or laser beacons aimed our way, or through the accidental leakage of their own technological activities, e.g., the waste heat from massive astrogeningery projects, or the atmospheric signatures of industrial pollutants on their planets, through the discovery of ancient alien artifacts, probes, or even evidence of past or present visitations. Yet, despite several decades of dedicated, albeit modestly funded, searching through projects like SETI, the Search for Extraterrestrial Intelligence, which primarily listen for artificial radio or optical signals from distant star systems, and despite the ever-increasing power, sensitivity and scope of our astronomical instruments across the entire electromagnetic spectrum, we have to date found no clear, irrefutable, and widely accepted evidence of any other technological civilization, past or present, beyond our own. This profound and persistent discrepancy between the high statistical expectation of the existence of extraterrestrial intelligence, often quantified by optimistic interpretations of the Drake equation, which attempts to estimate the number of communicative civilizations in our galaxy, and the stark empirical reality of its apparent absence, the Great Silence, forms the very heart and enduring intellectual challenge of to grasp the true scale, weight, and perhaps even the unsettling nature of this paradox. Consider the following analogy. Imagine you are an explorer who has just arrived on the shores of a vast, newly discovered continent. A continent that geographical and ecological models predict should be teeming with complex animal life, and perhaps even sophisticated organized societies. However, as you begin to explore this vast new land, using all your senses and the most advanced detection equipment available, you find nothing. No footprints, no birdsong, no distant smoke from campfires, no signs of agriculture or construction, just an eerie, inexplicable silence, and an unnerving emptiness where vibrant activity and complex life should, by all reasonable expectation, be present. This is somewhat akin to our current situation in the search for extraterrestrial intelligence. Given the immense number of potential habitats and the vast timescales involved, the persistent lack of any discernible evidence of other civilizations feels both deeply perplexing and, to some, profoundly unsettling. Several key factors contribute to the formulation and the perceived intellectual strength of the Fermi paradox. The sheer number of stars and potentially habitable planets. Our Milky Way galaxy alone is estimated to contain anywhere from 100 to 400 billion stars. Current exoplanet statistics suggest that planets are extremely common, and that a significant fraction of these stars likely host planets within their habitable zones. If even a tiny fraction of these potentially habitable planets actually develop life, and a tiny fraction of those develop intelligent technological civilizations, there should still be many thousands or even millions of such civilizations in our galaxy, and our galaxy is just one of perhaps 2 trillion galaxies in the observable universe. The sheer raw numbers suggest a staggering number of potential cradles for life and intelligence across the cosmos. The immense age of the universe and our galaxy. The universe is approximately 13.8 billion years old, and our Milky Way galaxy is nearly as ancient, having formed over 13 billion years ago. Our own solar system and Earth are relative newcomers at about 4.5 billion years old. This means that there has been an immense span of cosmic time, billions of years, for life to have arisen and evolved on other, older planets, potentially long before life even began on Earth. If other civilizations have emerged, some could be millions or even billions of years more advanced than our own relatively young technological civilization. The potential for interstellar travel, colonization, or large-scale engineering. Even with the vast interstellar distances involved, it has been argued by proponents of the paradox that a sufficiently advanced and motivated civilization, even one expanding at a relatively slow pace, say a fraction of 1% of the speed of light, could theoretically colonize or at least explore a significant portion of the entire galaxy within a few million to tens of millions of years. This is a relatively short timescale compared to the multi-billion-year age of the galaxy. If even one such civilization had arisen in our galaxy long ago, its presence, or the presence of its probes or artifacts, should be widespread and detectable by now. If not physical travel and colonization, then perhaps large-scale astroengineering projects like Dyson spheres, designed to capture a star's entire energy output, should be visible, or at least their waste heat detectable. However, the Fermi paradox is not without numerous potential, though almost entirely speculative and untestable at present, solutions or explanations. These proposed resolutions attempt to reconcile the high probability of extraterrestrial life with our current lack of evidence, and they range from the mundane to the deeply profound, and from the optimistic to the rather pessimistic. Some of the major categories of proposed solutions include: they don't exist, or are exceedingly rare, itself is an incredibly improbable event, or the subsequent evolution of complex, multicellular life, or the development of intelligence and technology, are all subject to one or more great filters, as we'll discuss next, that make us exceptionally rare, or even unique, in the galaxy. This is often called the rare Earth hypothesis in its broader form. They exist, but we can't detect them, or haven't yet. Technological incompatibility Perhaps advanced civilizations use communication technologies that are far beyond our current understanding or detection capabilities. E.g., they might communicate using neutrinos, gravitational waves, or forms of physics we haven't yet discovered, rather than radio waves or light. They are too different. Their biology, psychology, motivations, or societal structures might be so profoundly alien that we wouldn't recognize their signals or activities even if we encountered them. They are hiding or choosing not to communicate. Perhaps they are aware of us, but are deliberately avoiding contact for reasons of their own. This is the zoo hypothesis, or the prime directive idea. They might be observing us without interference, or they might consider us too primitive or dangerous to interact with. We haven't looked hard enough, long enough, or in the right way. Our search for extraterrestrial intelligence, SETI, is still a relatively young endeavor with limited funding and scope. We have only searched a tiny fraction of the available parameter space, stars, frequencies, signal types, etc. The galaxy is vast, and we might simply have not yet pointed our instruments in the right direction, at the right time, or with sufficient sensitivity. They existed, but are now extinct. Perhaps technological civilizations, once they arise, tend to destroy themselves relatively quickly on cosmic timescales, through nuclear war, environmental collapse, uncontrolled artificial intelligence, pandemics, etc. If the average lifespan of a technological civilization is short, then the chances of two or more such civilizations in the same galactic neighborhood at the same time might be very low. They are here, but we don't realize it. This category includes more fringe ideas, such as them being present in a form we don't recognize, as post-biological digital entities, or in other dimensions, or that evidence of their presence is being deliberately concealed. In conclusion, the Fermi paradox remains one of the most intriguing, humbling, and intellectually fertile, unanswered questions in our ongoing exploration of the universe and our place within it. Despite the compelling statistical arguments that suggest our galaxy should be teeming with life and intelligence, the conspicuous and persistent silence from the stars challenges our deepest assumptions about the nature of life, the trajectory of evolution, the destiny of civilizations, and the very meaning of our own solitary, or perhaps not so solitary, existence in the vast, silent expanse of the cosmos. Whether the ultimate solution lies in the intrinsic rarity of intelligent life, the insurmountable barriers imposed by some great filter, the deliberate silence or incomprehensible nature of advanced civilizations, or simply the current limitations of our search efforts, the paradox continues to fuel our scientific curiosity, drive our technological innovation in the search for answers, and deepen our contemplation about our role and our future within the grand unfolding narrative of the universe as we continue to advance our ability to explore the cosmos and to understand the conditions for life. We may yet uncover clues that will begin to resolve this profound enigma, an answer that could fundamentally reshape our understanding of ourselves and our place in the grand cosmic order.